Next, we have Brian Jacob. He's the CTO and the founder of Data.World. He is a leader in building large-scale consumer internet systems and an expert in data integration solutions. He has 20 years of experience in academia and professional experience spanning Case Western Reserve University, Trilogy, Amazon, and most recently building HomeAway.com. So welcome.
Thank you. Thank you. So yeah. Thanks to Wolfram for inviting me here, and it's really great to be able to address this audience here. You guys this is a really smart group of people to get to address, so I'm honored. Thank you. To build the web of linked data, we have to start by connecting the people who are working with data. I truly believe we're going to build a global web of knowledge. And when I think of it, I think it's going to be like the Starship Enterprise, when Jean-Luc Picard says computer and asks a question in English and gets back an answer. And you see that today a little bit with Siri, with an Echo, but and all that natural language processing that goes into that is great. It's amazing technology, but that's the keyboard, that's the interface. The reason why you have things like Wolfram Alpha that can answer a much richer set of questions, and the reason why the future is going to be the Star Trek computer is because of the connected database that sits behind it. And the technology that's going to build that already exists, has existed for years. It's the same kind of stuff that goes into a lot of the Wolfram suite. It's the technology of the semantic web and of linked data. Back in 2009, Tim Berners-Lee came on the stage at TED and said, "We haven't got data on the web as data." And he went in and explained what he means by that. He defined what he means by linked data for that audience there. It's fundamentally three things. One, give a unique identifier to everything that you're talking about, and specifically give URLs to talk about the entities in your data. Two, when you dereference that URL, give me back structured data in a standard format that I can consume and I can parse programmatically. And three, represent the relationship between entities as links between those URLs. And if everybody would just do that, we would have this global web of linked data. And this was the quote he left the folks at TED with. And this is the guy who invented the web. And he's basically standing there in front of this audience and saying, guys, this isn't even really anything yet. This web of documents we've created, it's great, it's brought people together, but the real power is actually to come when we can actually get at the underlying data in the same way. So why in 2016, 7 years later, are we've made some progress, but there are 18 million open data sets on the web today, and practically none of it works like this. Linked data is all about getting the network effect going with respect to data. So we all know how networks work. If the network is small, the value to adding your node to it is relatively small. But the cost of picking up on these technologies can be really high. And data scientists and business analysts and CIOs aren't necessarily that interested in paying this cost when the value they see is pretty low. But as the network gets larger, that value starts to increase and literally increases exponentially. The cost stays the same or goes down. And eventually, you're going to connect all this data together because it would be foolish not to connect your data to that resource. And the biggest, richest organizations in the world and the 1% of people working with data, they get this. It's why organizations like Google and Facebook base a huge amount of their infrastructure on this. BBC, almost all of their syndication is based on semantic web technology. Goldman Sachs' entire internal data warehouse is based on RDF, and that's true across a huge swath of financial institutions. Government institutions like the CAA, who are doing deep network analysis to assess threats, use this technology. But the problem is that 99% of the people who are working with data aren't aware of this technology, don't use it as part of their day-to-day. So I think three things have to happen to start getting that flywheel going and moving us closer to a world where we're actually building up this web of linked data. One, we need to connect the social networks of people actually working with data together. We need to grow the data superconnectors that can help increase the number of connections between data. And we need to build a bridge to linked data. So, number one, connecting the social networks of people working with data. Gartner's recent report tells us that the self-service data preparation industry is going to be $1 billion industry by 2019. Today, data preparation work, building pipelines using Python and Pandas and R, tools like Spark, a huge number of commercial tools. These are huge areas of investment and interest today, and that's only 5% of the market. 3 years from now, it's going to be at least 20 times bigger. But the vast majority of the work that those folks are doing, which is extracting knowledge, making sense of data so that they can use it to build their data products and perform their analyses, is being kept in data silos, or worse, just getting thrown away at the end of every project. Linking data together requires adding that knowledge to data about how it relates to other data sets. But knowledge engineering is generally being done, formal knowledge engineering is being done top-down by the 1% of people who are actually focusing on that technology. Most people are generating CSVs and Excel spreadsheets or downloading from open data portals. The words ontology and taxonomy are not part of their day-to-day vocabulary, but they are building these pipelines and they are adding knowledge to data, and we can capture that and turn that into linked knowledge. If we can link the minds of all those people together, that can be the engine that can start to actually build the web of linked data. But that social network, that connection of people today, needs to add value to the people who are working with data the way they work with it today. There are a set of common problems that everybody working with data, trying to perform analyses, has. I call it the who, what, when, where, and why of working with data. First of all, who provided this data? Central to the semantic web is the notion that anyone can say anything about any topic. What's meant by this is, just like on the web today, I can't prevent somebody from publishing data that is false or misleading or that I just don't like. If you have a web of linked data and everyone can contribute to it, you can't stop somebody from saying anything that they want to say. That's actually why you want to have strong standardized identifiers for the things we're talking about, so that we can know that you and I are talking about the same things, even when what we're saying is different. Just like on the web, the consumer's in control here. You can get around this in a decentralized way because you can control the sources that you want to pull your data from. So you can only go to a particular database that you know the provenance of and you know that you can trust. And a social network, to bring more data people into the world of data, needs to give folks that same sense of identity, where they can attach their work and align it with their identity. And those identities can form handles that can be used in the rest of the context that goes around data, the conversations and the chains of provenance that go with data. What is this data about? Data needs context to be able to understand what's inside of it. A CSV without a data dictionary or some amount of documentation isn't generally going to be useful to you if you don't have explicit knowledge of what's inside of it. Working with people the way they are today, the way they're working with data today, means letting them put textual descriptions, attach PDF documentation, images, videos, whatever's necessary to convey the meaning about that data. But turning that into linked data means giving folks the tools to iteratively take that out of band context and move it in band in a way that can actually help them get their work done. Where did this data originate, and when did this data last change? Data provenance is something that everyone working with data needs to understand or needs to deal with, even if they don't really understand what that is or call it that. And the vast majority of people out there don't. But you need to know what's the history of this data. You need to be able to deal with the fact that this data might change, and I might have to, and there might be new additional facts added to a data set. You need to deal with the fact that multiple data sets might have a single point of origin, and things branch and go down different paths. And you need to be able to externally link to a particular version of a data set, not just the latest version, but to a particular arbitrary version of a data set that you use to produce your research. And finally, why should I use this data? There is so much data on the web, and finding it, digging through Google can be a real challenge. how do I know which data set I should use and why I should use data set A versus data set B? Features like following another user, liking a data set or a query, these are casual, fun features, and it's easy to kind of dismiss them, but really what they are, at scale, in a platform where users are actually able to work with data, they're an incredible mesh of signals. They can classify users in their work, they can help identify cohorts so you can find the things that are most relevant to you, and they can help identify the data and the users that are the biggest connectors that actually can help you find more sources of data. Number 2, growing data superconnectors. In any network, the more highly connected nodes help grow the network more quickly. Just like in a network of people, the people with more connections are more likely to introduce two people who would have never otherwise met. The same is true with data sets. On the linked web today, DBpedia is probably the biggest superconnector. It's a linked database that's produced from a number of sources, but most notably by scraping all the structured data that they can extract from Wikipedia, so that as people are collaboratively editing Wikipedia, the data that they're entering that can be parsed out is pulled in and made queryable. And to build the web link data, we need to foster these superconnectors. We need to make them more visible, and we need to create more of them. Most of the superconnectors in data actually don't exist today as linked data. The previous speaker was talking about the American Community Survey. The ACS is produced every year by the US Census Bureau. It's a sampling of roughly 1% of the population to give you a relatively up-to-date slice of changing demographics. And it's already a data superconnector. He mentioned the top 100 direct users. There's thousands of people. There's a community online of people who work together to use this data resource. It's published today as a directory full of CSV files and a textual data dictionary. And it's a hugely valuable data set, but that data dictionary has a lot of out-of-band information. You really kind of have to become an expert in all the different ways that you slice and dice and aggregate that data in order to make a lot of sense of it. So one thing that we've been working on is building a linked data model of the American Community Survey. We built a fairly straightforward data pipeline. We wrote a bunch of Python code that takes that textual data dictionary, generates a raw RDFS schema. We do a lot of manual work on that to really get in there, to understand the concepts, straightforward knowledge engineering, data modeling work. And we produced an enhanced schema that describes the same concepts that were built into the data dictionary. We then wrote a separate set of code that takes the raw CSV data itself, converts that into an RDF model. We have a pipeline that we use, Sparkle, which is a query language over RDF data. We wrote a pipeline of 75 Sparkle queries that iteratively takes chunks of that ACS data and aligns it with the concepts in that enhanced schema, so that at the other end we have the ACS enhanced data. So the net of all this is, we took the raw ACS data, which is a bunch of CSVs, and some text that you can read, that you can understand, and you can reach out to a community of people to help you understand, and turn it into a linked data model where that context from the data dictionary is embedded in the data and can be queried alongside the data. Just as a couple quick examples of what this looks like in practice. So this is a snippet from the state code from that data dictionary, and every state plus the District of Columbia is coded with a 2-digit numeric code, so that you can read that text file and you can know that, oh, I get it, when this column says 11, that means DC. And this is what the corresponding entry in our enhanced schema looks like. We've defined a URL for that state. We've given it type information. We've added attributes like the abbreviation for DC and the label of District of Columbia. That basically represents a knowledge graph where the state itself and the values of all of those properties are nodes in a graph, and the edges of the graph are labeled with the names of the properties. Another very quick example. 2 Boolean properties I pulled out from the ACS data dictionary. One represents whether a housing unit has complete kitchen facilities. The other represents whether the housing unit is a multi-generational household. The interesting thing, the reason I pulled these 2 examples out, is that in the first case, 1 codes for yes and 2 codes for no. And in the second case, 1 codes for no and 2 codes for yes. In the enhanced model, I've defined 2 properties. I've called I've stated that these are object properties. I've said that their domain is housing records. I've put the text label that describes what the property is inside of the data itself, and I've normalized these to a Boolean value so that the value is either true or false. This is all relatively straightforward stuff, and the upshot of having gone through all of that is that I can now write this Sparkle query, which is very straightforward if you understand Sparkle, like me and tens of other people, and not that straightforward if it's not something you're that well versed in. But what's really interesting isn't so much that I can write this query, which is telling me how many millennials there are per state, and I could slice that by any of the other, any of the other variables and dimensions in that data. But because I've now got this as linked data, I can start to write federated queries where I could join this data directly against what's in DBpedia or against any other data set that is represented in that as an RDF model. So number 3, building a bridge to the web of linked data. If the vast majority of people are not linking their data because they don't get enough value in return for the cost of doing so, or in many more cases, they don't even know what that means. It's not even on their radar. Then we need to reach out to them with tools that make sense to the way they're doing work today and bring them to that web. So imagine, as an example, a data scientist named Alicia. She wants to perform an analysis comparing crime rates in the DC area versus median household incomes. So she goes to an open data portal and downloads a CSV, and she goes to the American Community Survey and she grabs a CSV for the DC data. And she's a Python programmer, so she codes up her Python pipeline that takes those CSVs and produces a resulting projection across them. And now she can produce her analysis and publish it. And she's happy and she's done. But when she's done that, she's actually added some knowledge about what's in that open data CSV that she pulled off of a portal and what's in the ACS. And that knowledge, in almost every case, is just lost. No one else can benefit from that having been done, because out the other end of that pipeline, she produced her analysis, and the rest of that work is getting thrown away. If we can bring all of the Alicias of the world, all the data scientists, together and give them a way to communicate and give them a way to preserve that work for posterity, they can bring the document-based way they're looking at data today to the system. We can convert that to linked data, and we can give them the tools so that the work that they're already doing with the tools they're already familiar with are going to start to create those connections. And we can still allow users to work with that data through the same kind of abstractions they're used to working with, the same tabular data structure. Because ultimately, the vast majority of data that data professionals are working with is tabular data. And so the way we look at tabular data in our systems, and I think as a way to bridge any data professional to linked data, you can model tabular data just like you can model any other type of data. Tables can be entities, columns and variables can be entities. You can model observations of variables as relationships between cases, which are entities, and the values in the cells of a table. You can annotate variables and columns and tables with descriptive information, with type information, with things like indexes that can allow you to render the data back to something resembling its original format. You can start to layer data. you can start to look at the fact that I've got a zip code column, and it's a bunch of 5-digit numbers as strings, but really a zip code is a thing, it's an entity, it's a concept, it's a thing that we should have a shared taxonomy on, so that everyone who is slicing and dicing their data by zip codes is slicing and dicing their data by the same zip codes, and those represent relationships to entities. A lot of the common practices that data scientists do fits very well into this model as well. Cleaning compacted data, the value 1x750 ml isn't something I can do a lot with computationally. But if I know that that represents I've got one 750 milliliter bottle of wine, I can now take that data and I can do unit conversions and I can do computation on it, and I can combine it with other sources of data. The inverse of that, I might often have data that's been broken up. So I might have month, day, year columns, and I'd like to be able to combine that to a date value so that I can do data arithmetic to it. The key here is people do this kind of data cleansing all the time. They do it isolated in local context, and they throw that insight away. The fact that these values can be usefully combined to form a date value is generally not retained along with a data set. What you can do is you can model this as a new variable that becomes part of the data set. The function to produce it can become part of the data set, and this can live with the data as context that can be useful to the next person who comes along. One final example, just thinking about a common statistical operation like binning variables. When you're binning a numerical variable, what you're really doing is you're defining a new set of categories, and you're allocating cases of your variables to those categories based on a numeric value. Those categories are things. They can have a URL, they can have a unique identifier, and you can attach attributes to them. So you could, for example, label the categories, you can define the boundaries of it, you could even do some upfront statistical analysis of the data so that you can have pre-computed statistics already attached in a knowledge graph or attached to the data. So that when the next Alicia comes to do her project and she brings up her linked data version of the crime statistics and makes the connection to the ACS data, and John, another data scientist who's working on a project to analyze the performance of schools in the DC area to decide where he wants to move to send his kids. And he's done the work to connect up to the ACS so that he can break that down by household income, by racial demographics. He can make the connection that, geez, it would be great if I could also look at those schools and look at the areas I'm thinking about living, broken down by those crime statistics. To build the web of linked data, we have to start by connecting the people who are working with data. And I think if we can connect the social networks of people working with data, grow the superconnectors on the web of linked data, and build a bridge from the way people are working with data today to the way that we'd like them to work by connecting their data and applying knowledge to it, then we can actually build the web of linked knowledge, not just for the 1% of people who get it, but for and with the 99% of people working with data who can help get it done. Thank you.